Now I call Leka Pandi for the brief introduction about our resource person to the participants.
Thank you, sir. Good evening, everyone. It is a privilege to welcome Mr. P. Sivaraman, Senior Member IEEE and Power Plant Control Engineer at Schneider Electric Solar India Private Limited. With 10 plus years of experience, he specializes in power system studies, renewable energy compliance, and power quality analysis. An expert in ETAP, PSCAT, DigiSilent, Power Factory, and PSSE, he actively contributes to IEEE standards and serves as project coordinator of IEEE ADSF site. A prolific author, he has authored and co authored 6 books and published several research papers internationally. We are honored to have you with us, sir. Welcome.
Thank you, Anulika. Thank you all. Thank you everyone for joining this session. I hope you will enjoy this session. Shall we start? In just a minute, I will share my screen. Just a minute. It's loading. Just a minute, please.
Sure, sir.
I'm sharing my screen. Let me know once it is visible to you.
Yes, sir, it is visible, sir.
Yeah, sorry, I opened a simulation model in the background, so it took some time. Sorry for that. Thank you everyone for joining this session. I will start with this session. This session is about the harmonic analysis for the IBR plants. So IBR means an inverter-based resources. Typically, a solar power plant, wind power plant, and power plant with battery energy storage system uh, generally considered as an IBR system. So in this session, I will take you through the harmonic analysis. What are the types we can perform the harmonic analysis for IBR plants, and some examples how we can do it. About myself, I'm Sivaraman. I'm a senior member of IEEE and a project coordinator of IEEE ADXF site. So presently I'm working with Schneider Electric. Can anyone confirm my screen is visible to you?
Yes, sir, it is visible, sir.
Yeah, good. So the outline of this presentation, I will give some introduction about power quality, then about harmonics, and about the IBR plant. So typical IBR plant, how it looks like. Then how to perform the harmonic analysis, then harmonic analysis, how we can do it through the power quality analysis through the at the site, and the harmonic analysis using the software simulation. So moving further, power quality, it's one of the important concerns for an electrical system, especially the AC system. So generally, the power quality can be defined as any problems in voltage, current, and frequency deviations. Any deviation happened to the ideal characteristics of the voltage, current, and frequency. This is generally called as the power quality problem. This problem will resulting to failure, mal-operation, or increased energy loss, premature equipment failure, lifetime reduction. So, due to poor power quality, any of the things may happen, like premature failure or mal-operations, etc. So about the power quality characteristics, as per IEEE standard 1159 in the year of 2019, this is the latest IEEE standard published in 2019. As per this standard, the power quality characteristics are transient, short duration voltage variation, long duration voltage variation, imbalance or unbalanced, and waveform distortion, voltage fluctuation, and power frequency variation. So these are all the seven majorly categorized power quality problems. So the harmonics comes under the waveform distortion. So this is the table which is given in IEEE 1159. So in that, in transient, there are two types are there: impulsive transient and oscillatory transient. And in the short duration voltage variation, in that instantaneous, momentary, and temporary, in that voltage sag and swell, also interruption parameters are there. So the corresponding duration and magnitude they have given in the right side. For an example, short duration variation, the instantaneous sag, it will be called as instantaneous sag if it is happened at between 0.5 cycle to the 30 cycle. The RMS voltage reduction between 0.9 to 0.1 per unit of voltage. And long duration voltage variation, it is an sustained event. The event greater than more than 1 minute of time duration, and generally this event is called as long duration voltage variation. So compared to the short duration voltage variation and long duration voltage variation, short duration voltage variation, the maximum time duration is 1 minute, and in long duration voltage variation, the event which is happening after 1 minute, generally it's called as long duration voltage variation. Then about the imbalance, so it also voltage and current imbalance. So the typical magnitude is available here. So for an voltage, it is 0.5% to 5%. And importantly, our topic is comes under the waveform distortion. So here two parameters, harmonics and interharmonics. So that is our topic. So harmonic is fundamental frequency of 50 hertz or 60 hertz generally are called as harmonics, and interharmonics, it's what are the harmonic component which is not the integral of multiplies of 50 hertz or 60 hertz are generally called as interharmonics. And voltage fluctuation and power frequency variation. So I am not going to touch about that. So continuing further about the harmonics, generally our power systems are operating at sinusoidal voltage and current characteristics before 30 to 50 years before. So I remember the year of 1960s onwards, the introduction of power electronic based converters introduced into our electrical power system. So from that time onwards, the harmonics become an important concern, because these power electronics based equipments are generally non-linear devices. So it will draw a non-linear current from the sinusoidal voltage during their operations. So since the non-sinusoidal current drawn from the voltage, it resulting to voltage also, the sinusoidal voltage also become distorting to the non-sinusoidal. So in nowadays we are having more number of non-linear equipment, starting from our mobile charger, laptop charger, our TV. So to the power electronic based high power equipments like VFD drives, solar inverter, converters applications in wind applications, then battery energy storage system applications. So nowadays power electronic based devices keep added into our power system. So it is an important concern nowadays, because the harmonics having a negative impact to the power system. So generally the harmonics are called as integral multiples of fundamental frequency. Considering a 50 hertz of fundamental frequency, any frequency component which is higher than or lower than the fundamental frequency of 50 hertz or 60 hertz are generally called as harmonic frequency. So these harmonic frequencies are created by the non-linear devices like power electronic based converters during their operation. Those frequencies will get added into the fundamental frequency. So due to that, the fundamental frequency gets distorted. So in this figure, the black color line, it's a fundamental frequency. Let's consider it is an 50 hertz. So and it having a 3 harmonic component: third order, fifth order, and seventh order. So third order means 3 times of the fundamental frequency. Fifth order means 5 times of the fundamental frequency in one cycle. Right? So in this figure, the fundamental frequency is one cycle. In that, third order harmonic will complete 3 cycles. So the yellow line is the third order. Within one cycle of fundamental frequency, it will complete 3 cycles. Similarly, for the fifth order, it is in blue color. Within one cycle of time period, fifth order will complete 5 times. So what it will do, it will degrade the ideal sinusoidal characteristics in voltage and current. Here the black color is the sinusoidal voltage. So in which the 3 harmonic content, third order, fifth order, seventh order added into it. So due to that, the sinusoidal voltage get distorted. So the green color line is the resultant line. After adding the 3 harmonic frequencies into the fundamental component, the voltage is distorted. The green line is the resultant waveform. You can able to see there is an distortion, especially in the peak side. So there is in sinusoidal we are having only one peak. Here you can able to see we are having 4 peaks in the one positive cycle. So due to this, our voltage and current get distorted. The distorted supply is given to the end user equipments. So due to that, we are having negative impact, especially the premature failure. So generally, every electrical equipments having a predefined lifetime. Generally, it is 25 years, starting from a transformer or cables or any switchgear products. So most of the products are designed for a lifetime of 25 years. So due to harmonics, the electrical equipments may not able to come to the 25-year lifetime. Due to the harmonic characteristics, the equipment may get failed before the predefined design lifetime, and it will increase the losses, including power loss and the electromagnetic interference. So due to the harmonic frequency, the communication circuit get affected severely. So the reason is that electromagnetic interference. Whenever there is an electrical cable nearby, there is a communication cable. Due to the harmonic frequency, it will produce more amount of magnetic field. That magnetic field get induced in the communication cable. So due to the induction, the voltage in the communication cable get increased. So generally communication will operate in 5 volt to 12 volt only maximum. So due to this induction, voltage will get increased. Then finally it resulting to failure of the communication equipment. And the mal operation of the equipments like relays and what are the equipments which is operating based on the voltage sensing and voltage switching. So generally there are some devices which will switch based on the voltage, especially when they are coming to 0, that time it will switch on and switch off. So due to that, the equipment may mal-operate. So the main reason for the harmonics, mostly the power electronic based equipments like inverter, rectifier, chargers, cycloconverters, and arc furnace. So arc furnace not comes under the power electronic based equipment, but it also will produce the harmonics. So in addition to this, there are some other devices also will produce the harmonics, but it is not a normal operation. It will be an extreme operations. We know transformer is a linear equipment, so but the transformer also will produce the harmonics when the transformer core is saturated. So when the moment transformer core is saturated, the transformer also will produce the harmonics. Okay. Continuing further, the harmonic indices. So we have to, we know due to the electronic based equipments, we are having the impact due to the harmonics. So in our, we have to evaluate the harmonics. Then only we can able to limit the harmonic injection into the system. That is the one. And also we have to penalize based on the amount of harmonic injection. So suppose consider a scenario. So totally 10 customers are connected to the common electrical grid. So nine customer is controlled their harmonics. Only one customer is injecting the harmonic into the system means. So the other 9 customer also get affected. So for in this case, the company which is maintaining the electric power system has to penalize the customer which is producing the harmonics, right? So for that reason, we are having a harmonic indices or a harmonic evaluation method. The commonly accepted methods are total harmonic distortion. Total harmonic distortion is a summation of all the harmonic component divided by the fundamental component. So the total harmonic distortion, we can calculate it for the voltage as well as the current. The IEEE standard 519 also having the limit for the voltage harmonic distortion, especially for the voltage. Similarly, IEC also having the maximum recommended limit for the voltage in total harmonic distortion. And we are having 2 more harmonic indices called total demand distortion and the total rated current distortion. So IEEE standard 519 in the year of 1991, they introduced this terminology total demand distortion. So based on the amount of load we are connected and we are operating, based on that amount of load, the total demand distortion is calculated. So in the numerical value, starting from the second order to the till the maximum order, we will consider. But in the denominator, it is not a fundamental value. It is a maximum demand average value on the previous 12-month value. So this value is called as IL. That IL is maximum demand average load current. But in THT, it is a fundamental current. Okay. So why the TDD is introduced to means in the lesser loading time, absolutely the fundamental value will be very less. So if we calculate the THT at lesser loading time, the THT value will be normally high. So sometimes it will give an wrong evaluation. So for that reason only they introduced the total demand distortion. And continuing further about the total rated current distortion TRD, this metrics is introduced in IEEE standard 1547 in 2003 version. So this metrics only used for renewable power plant based applications. So total demand distortion TDD is used for the customer having a load. So end user based applications, we have to use it TDD, and the renewable based applications, we have to go for the TRD. So in IEEE 519/2022, they are having a decision tree. If the customer having a internal load as well as the renewable generation, then based on the decision tree, we have to follow. So in TRD, we have to evaluate based on the rated curve. So in what is the difference between TDD and TRD? Means in TDD, we are considering the maximum demand average current, but in TRD, we are considering the plant capacity rated current. For an example, it is an 100 megawatt solar plant connected at 110 kV voltage level. Means for the 100 megawatt plant, what is the rated current is coming at 110 kV. So that value we have to consider as an I rated to calculate this TRB. So as of now, anyone have any doubt? If there is no doubt, I will continue further. If you have any doubt, please interrupt.
Participants, if you have doubt, kindly unmute yourself and ask questions. You can also put the questions in the chat box. Sir, I think you can proceed, sir.
Yeah, okay, fine. So about renewable power plant, renewable power plants are generally called as IBR plant. IBR means inverter based resources. As I told, this renewable IBR plants consist of solar plant, wind plant, and battery energy storage system. Maybe a hybrid plant, including a solar with the battery energy storage system, or wind with the battery energy storage system, or any of the three combinations. Okay, so this one is the typical single line diagram of the solar plant. I hope it is visible to you. So I will explain here. This is a typical single line diagram. This one is the solar PV panel. Solar PV panel, and this component is the representation of the inverter. This is the representation of the low voltage bus. So generally, for the utility scale application, so we are having three type of solar inverter. One is the central inverter. Normally, it will be in megawatt range. Up to nowadays 4 megawatt it is available. And the second one is the string inverter. String inverter generally in kilowatt range, starting from 1 kilowatt for rooftop application to 200 kilowatt, 250 kilowatt. It is available for the utility scale applications. Utility means large scale applications in megawatt scale. Then third one is the micro inverter. As the name implies, micro means a small rating inverter. So generally, the micro inverters are available in the range from 250 watt, not kilowatt, 250 watt to 1 kilowatt or 1.5 kilowatt. It is available. So based on the reliability, we have to select what type of inverter we are using in our power plant. Okay. Then this is the inverter duty transformer. So generally, the low voltage side, that is the inverter terminal voltage, generally it's from 500 volt to 690 volt. So in the inverters which is came in the between the year from 2013 to 2018. So mostly those inverters voltage are around 500 volt. Nowadays, most of the inverters are coming with 690 volt. So that is the general terminal voltage of the inverter. And the inverter duty transformer, the typical inverter duty transformer LV voltage is the solar inverter terminal voltage. Consider example 690 volt. And the high voltage side, it will be at 11 kV or 22 kV or 33 kV. 11 to 33 kV. Suppose the plant is connected to the medium voltage. So what is the medium voltage value? That value, the HV side voltage will get decided. Most of the utility scale application in megawatt range, for an example, 50 megawatt and above, mostly it will get connected through the 66 kV voltage level and above. So 66 above means 110 kV, 132 kV, 200, 220, 230, then 400. For an Indian voltage level, it will get connected. So in most of the time, here the high voltage bus, the plant interconnection bus voltage will be according to the interconnection voltage available at the location. In this example, it is an 110 kV. The medium voltage, that is the transformer output high voltage side is at 33 kV. So what it will do, this transformer will step up the voltage from 690 voltage to 33 kV, and it will get connected to the main transformer. This is a main transformer in a solar plant. So it is an 110 or 33 kV transformer. So it will get connected to that. So typically this connection is called as collector network. So what it means is that for a large scale plant, we are having more number of inverters. For example, for a 100 megawatt plant, if you are using a 2 megawatt inverter, so it means we are having 50 number of 2 megawatt inverter. So we have to connect all the 50 number of 2 megawatt inverter to the main LV 33 kV bus at the substation. So for that, this collector network will be used. So generally, this collector network may be a cable or maybe a transmission line, 33 kV transmission line. So that be a cable also, sometimes it can be a transmission line also, maybe a combination of the both. Okay. And it will have a power transformer. It will step up from 33 kV to 110 kV. So the 110 kV it's an interconnected system. So 110 kV will come at this place. So there we are getting connected to the transmission system. From there we are exporting the power supply to the power grid. Okay, so continuing further, from here onwards, I will explain about how to perform the harmonic analysis and what are the data required, what are the methods available for the harmonic analysis. Okay, so for your information, IEEE standard 3002.8 it is published in the year of 2018. So this standard is for the commercial and industrial power plant harmonic analysis, but the information provided in this standard is applicable for all the type of harmonic analysis. So based on this standard, we can perform the harmonic analysis in 4 ways. One is the manual calculation. Second one is the conducting the field measurement at the site through the power quality analyzer. Third one is the model calibration, and fourth one is the computer simulation. There are some advantages and disadvantages are available in each of the methods. Manual calculation method, before the introduction of computer simulation, mostly our previous generation power system engineers done the harmonic analysis through the manual calculation. It is very useful for the simple system. for a complex system, it is extremely difficult to perform the harmonic analysis. And conducting the field measurement at the site, it is one of the practical way to measure the harmonics, how much amount of harmonics it's get injected. For an example, if we want to comply the harmonics at this 110 kV bus at this location means when the plant is operating, during their operation, how much amount of harmonics get injected by this solar plant at this 110 kV, that we can do it by this field measurement through the power quality analyzer. There are some limitations are there with conducting the field measurement. What it means is that we can able to capture the harmonic analysis only for the operating values. We can't able to do the harmonic analysis for different scenarios. So I will explain what is different scenarios in the coming slide. So that is one of the limitation. Model calibration means we can simplify our model. For example, in the entire solar plant model in a simulation software, and we can perform the harmonic analysis, and we can design a mitigation devices also. So this is called as a model calibration. Generally, this kind of model calibration will be done during the harmonic filter design stage. When there is a dispute between the solar plant, for example, solar plant to the electric power supply distribution company or transmission company, in those period only the model calibration type of harmonic analysis generally used. So this involved a simulation tool as well as the hardware in loop simulators like Opal RT, RTDS, Typhoon, Child, etc. And the fourth one is the computer simulation. So computer simulation, it's an electrical power system software like ETAP, Big Silent Power Factory, PSSC, Syncol, etc. So these software having the feature of representing the harmonics in the system, and we can able to model the each and every element present in the single line diagram, starting from the solar panel, solar inverter, inverter duty transformer, then collector network, then transformer, then transmission light. If any reactive power compensation device like capacitor, fans, statcom, reactors, we can able to model it, and we can able to do the simulation. In most of the time, computer simulation is the method widely used because it will not involve any of the practical elements. For an example, if you need to do the field measurement at site, means the site should be in operation, then only we can able to do. But when the plant is in planning and design stage, so you are the developer, you are going to develop a 250 megawatt solar plant in some location in India, means when you have some development planning in your mind, that time the computer simulation is the best method to perform the harmonic analysis. So the main advantage is that it does not involve any practical elements. That is the first one, and we can able to do n number of simulations. For an example, one simulation I am doing with the 2 megawatt inverter. Next simulation I am going to do with the 2.5 megawatt inverter. Next simulation I am going with the 3.125 megawatt inverter. Like that, I can do any number of variations in the simulation without much effort. That is the advantage of computer-based simulation, and also it will take lesser time compared to the other 3 types of methods. Okay. Continuing further, I will take you through the performing a harmonic analysis through the field measurement at site. So in this figure, what you are seeing is an power quality analyzer. This one is the power quality analyzer made of Dranex. The brand model is HTPQ X-Flow. So these elements, these equipments are the accessories. This one is the CT current transformer. So normally we studied that current transformers mostly an electromagnetic type. These CTs are not electromagnetic type. These CTs are Rogowski type. Rogowski coil, Rogowski principle is that. So these CTs are manufactured based on the Rogowski principle. So for the current measurement, and these for the voltage measurement, and these cables for the communication purpose. So nowadays, power quality analyzer we can able to monitor through the from the remote location whenever it is connected through the Wi-Fi or Ethernet line like this. So it is a typical block diagram. In this example, we have performed the power quality monitoring for 180 kilowatt solar PV inverter. It having a distribution transformer like this. It is connected to the 3 kV side and the high voltage side. It having the 450 volt in the low voltage side. So it having the internal load also. So the total aggregated solar PV capacity is 180 kilowatts. So the power quality measurement is performed at this location through the power quality measurement. So this is Dranex power quality analyzer we have used for the power quality measurement. So this is the voltage and current value from the power quality measurement. It is in the left one is the voltage and right side one is the current. And the measurement, this graph shows the value from 6 a.m. in the morning to around 5 p.m. in the evening. So in between the voltage in the 3 phases and the current in the 3 phases. Okay, so from this figure, almost 8 o'clock. This is the 8 o'clock period. So 8 o'clock only, the solar power generation start increasing. So at this point only, it start generating around 7 a.m. in the morning. So almost 8 a.m. It reached almost 25% of the capacity. So in this period only, we are having a maximum power generation, almost 216 ampere. It's recorded in the R phase. 218 ampere is recorded in the Y phase. About the power in the total power, it's delivered on that particular day. 154 kilowatt of power it delivered, and also it consumes amount of reactive power. So at this period, when the plant is operating at maximum power, that time it consumed some reactive power from the grid. Okay, and this one is the current THT. So current THT. So before the solar generation time, in the R phase, the THT is little bit high. So in this period, around the morning 6 o'clock, it is around 20%. Slowly, it's get reduced when the solar start generating. So here there is a slight increase in THT. Maybe this is due to the reduction in the power. So sometime back I told, right, why TTD method is used instead of THT. The reason is that during the lesser operating condition, it will calculate more THT. So this is the THT value. So you can able to see when the plant is delivering a very lesser amount of power, that time the THT value is a little bit high. So if you take this value for the compliance, then absolutely this is a higher value. So this is the nature of the power electronic converters. So in order to avoid this kind of situations only, the later part they introduced the TDD method. So during the peak generation time in this period, the THT maximum THT is 1.35 percentage. So generally, please remember, generally manufacturer who are all manufacturing the solar inverters will comply the THT of 3%, current THT of 3% at 100% of active power P. So they will comply 3% of current THT at 100% of active power. For an example, if it is 100 kilowatt inverter means, so 3 THT they will comply at 100 kilowatt only, 100 kilowatt only. For an example, it is operating at 20 kilowatt. For 20 kilowatt, whether if this inverter will produce the same 3% THT means, it's a bigger question mark. Most of the time, it will not produce 3%. It will produce closer to 6 to 9%. Please keep this is in mind. So now I will open a simulation software file. We have performed some power quality measurement at the site. So I will open that power quality measurement file. I will explain the values. So what are the values I shown in just before I will explain here. So this is an software from the Dranettes. So in the left side, the time plot here mentioned, right? So this is an RMS value. In the right side part is an peak to peak value. So I will explain about that. First, I will select the voltage. So first I will select the voltage in the left side. I just selected only the voltage RYB phases. In the right side, I will just display only the voltage waveform. Left side is an RMS voltage, right side is the peak to peak voltage. Okay, so in the left side here there is a red color dotted line, right? So in the particular dotted line, this is the voltage waveform is recorded. So I will come to at this location. This location closer to 1 p.m. So in this 1 p.m. only the solar plant is delivered at the maximum power. I will come to this location, this point. So now it is a little bit better. I will include a bar graph. I hope it is visible, right? Can anyone confirm whether you are seeing my screen with bar graph?
Yes, sir, it's visible, sir.
Yeah, okay. So what is the voltage waveform what you are seeing in the top side? The corresponding harmonic spectrum it's shown in the bottom figure. this one is the THT, and remaining central is a harmonic spectrum, second order, third, fourth, fifth, seventh. So here the maximum order is fifth, seventh, and 13th order is the maximum harmonic order. This is in voltage. So now I will plot to the current. So it is an interesting one, current. So, okay. So in the entire monitoring period, I will just select only the solar generation time. So in the solar generation started from the morning 6:50. So at this point only it started closer to this point. So generally you people heard that solar is an intermittent power generation in nature, right? So this is the best example to explain. So can able to see at no point of time it is delivered. The solar 180 kilowatt is delivered continuously. So the current is keep varying. So earlier from 110 210 ampere to in the next minute came to 101 ampere. So there is a variation. So this is generally a best example of intermittent resources. So I selected at the maximum generation time. So I will set this side. I will select to the current waveform. This is the current waveform. You can able to see there is an a light distortion in the current also. So I will plot here the current harmonic bar graph. So in the current harmonics, it is closer to 2% THT. The THT is almost 2%. So fifth order and 13th order is the maximum harmonic orders. And after that, 17th order and 19th order also it is contributing higher value. Okay, so I will plot three things. First one is the power. So I will plot the total power. So it is closer to 153 kilowatt. And the next one, what I will plot the current THT in R phase. Current THT in R phase. So current THT when it is operating at closer to 123 kilowatt. So that time the current THT is almost 2%. You can able to see. So I will little bit unzoom and I will go to this point. It is closer to 75 kilowatt. So in the 75 kilowatt, current THT is little bit, THT is almost 2%, but individual order is changed. Then I will go to this location where the lesser amount of power is delivered. So at this point, it is totally delivering a 45 kilowatt only. So for that period, you can able to see the current harmonic distortion. We can able to see, right. We can observe a good amount of harmonic distortion in the current waveform. And also the harmonic distortion is increased. Earlier when it is delivering at 123 kilowatt, that time it is 2% THT. Now it is almost 4% THT. Okay, so what is this? 13th order, it's contributing almost 3%. Okay. Do you have any doubt as of now? If you have any doubt, please let me know. There is no doubt. I will continue further about the power quality measurement. The power quality measurement, the analyzer, and the accessories, current city and voltage, PTs and cables. We have to connect at the where we want to measure the harmonics. For an example, for this power plant, the 110 kV voltage is the point of connection. In those location, in this location only, we have to complete the harmonic measurement. So it means we have to connect the power quality analyzer at this location. So this power quality analysis generally made for the voltage up to 1 kV. Whenever the voltage is going more than 1 kV, we have to connect this power quality analyzer to the available CT and PT at the site. So in the CT and PT, they will have a reduced voltage and current. Mostly the CT will be 1000 ampere bar 1 or 1000 ampere bar 5. So we two secondary current will be there, 1 ampere or 5 ampere. So we have to connect it at 5 ampere or 1 ampere side. And in the PT voltage, so 110 kV bar 110 volt. So in the voltage side, step down transformer, normally we will use it for the measurements. So it will be connected to the 110 kV and its secondary voltage will be 110 volt. So we have to connect it to the 110 volt, the CT and PT, and we have to modify the settings in this. So in the analyzer, there is a scale factor based on the CT ratio. We have to enter CT and PT ratio. For an example, 100 ampere CT in the primary, 5 ampere in the secondary means 100 by 5 we have to enter in the scale factor. So what it will do, 100 by 5 is 20. So how much amount of value is reading, it will multiply the 20 on it and it will record it. Similarly for the voltage also, 110 kV bar 110 volt means how much is the value is coming. So that value we have to enter it as a scale factor. Then it will calculate accordingly, right? Then continuing further about the harmonic analysis using the software simulation. As I told, there are dedicated power system simulation softwares are available in the market. Silent Power Factory, ETAP, PSSC. There are other software also. These are all some of the softwares widely used in the market. So for doing this software-based simulation, there are certain steps involved in it. We have to do the steps one by one. So the first one is the building the single line diagram. So first we have to model the single line diagram as per the actual plant. So even though in the plant planning stage or design stage, we should have a plant layout and a tentative single line diagram. So based on that, first we have to build the single line diagram in the simulation software. And the second one is the equipment modeling with actual value. So equipment modeling means it involves the solar inverters, inverter duty transformer, cables, then transmission lines, transformers, and capacitor banks or reactors, etc. So, what is the cable length? What is the size of the cable? What is the impedance of the cable? How many number of runs we are using for the transformer? What is the rating of the transformer? What is the impedance of the transformer? Whether any OLTC is there or not there, or any off-circuit tape changer is there? What is the tape size? What is the tape step, etc. We have to model in the single line diagram. Then next one is the modeling of harmonic source. So we have to model the harmonic source. In a solar plant or wind plant, the major harmonic source is the solar inverter or converter in the wind turbine generator. So that we have to model. Generally, we can model the harmonic source in two methods. One is the Thevenin equivalent, or another one is the Norton equivalent. So in the Thevenin equivalent, we will model the current harmonic spectrum in a voltage with series impedance. In a Norton equivalent, we will model as a current source as a parallel impedance. So this is an important method step. And the next one is the model of the grid data. So grid data means in this diagram, so here we are having a grid representation, right? So we have to model. So what it means, the entire power system, how we are representing in the simulation software. So normally we are having two methods. One is the single machine infinite bus system, and another one is the multi-machine infinite bus system. So we want to consider accordingly. We have to model. So in most of the harmonic studies, we will model as a single machine infinite bus system. In some extreme cases, we will model as multi-machine infinite bus system. Okay. And next one is the location of the compliance. So most of the standard and the grid code as of now, mostly they specify the grid interconnection point as the compliance point. The previous example what we seen, right? There it is a 10 kV, it's a compliance point. So in that location, we have to comply the harmonics and allowable limits. So we want to know what is the compliance location and what is the allowable limits in both voltage and current harmonics, including the individual harmonics as well as the total harmonic distortion or total rated current distortion. Then we have to perform the harmonic analysis for various grid operating environments. Like for an example, the grid voltage totally depends on various factors, right? So it can able to operate from the minimum value to the maximum value. For an example, if you are having a 10% tolerance, means in the positive side also it can go to 10%. In the negative side also it can go to the 10%. So within that band it can able to operate. So that we have to consider in the simulation. And importantly, grid strength. So whether it is a weak grid or strong grid, so that we have to model. In a strong grid, will be resistant to the harmonic order, harmonic injection. In a weak grid, it is very much important because the smaller variation, the current distortion will be high. That we have to model. And the grid operating impedance, like contingency scenarios, how we are performing n contingency, n-1 contingency, n-2 contingency. So like that, the utility power system operator will perform the n-1 contingency or n-2 contingency. That also we have to consider. Then after performing the harmonic analysis, we have to evaluate the individual as well as the total harmonic distortion against the allowable limit. So these are the typical steps involved. So about the modeling of the harmonic source, as I explained, we have to model in Thevenin equivalent or not on equivalent. Mostly, we will model the harmonic source as a not on equivalent. So you see a current source with parallel impedance. So the inverter manufacturers will provide this value. So for an example, this is a second order harmonics. So for the second order harmonics, what is the current it will inject at this location? For an example, it is 1 ampere. Then what is the impedance for the second order? Let's assume it is 0.3 ohm. So this value, the individual equipment manufacturer needs to provide, in which make we are using for the particular site, we have to get it from them. Okay, so we have to consider up to 50th order minimum. So second order harmonics to 50th order, we have to consider minimum. If more than 50th order also the particular inverter is producing, means we have to consider more than 15th order harmonic also in the modeling. Okay. Similarly, for the Thevenin equivalent also, in the Thevenin equivalent, mostly we are not modeling. In a rare case only we will model. The reason is that solar inverter or wind converter or battery converter, mostly a power electronic device, it is a current source, not a voltage source. So current source modeling representation we can easily achieve through Norton equivalent only, not through the Thevenin equivalent. So Thevenin equivalent means with the current source and the impedance, we have to convert it to the voltage source and we have to model as a voltage source. So that will involve an additional step, so that normally we will avoid. Okay. So I will take you through simulation in Dixile and Power Factory. So I am at this moment I am presenting a simulation software Dixile and Power Factory. Can anyone confirm you can able to see a simulation screen instead of presentation?
Yes, sir. Visible, sir.
Yeah, okay. So this is an Dixile and Power Factory simulation software. It is an licensed version. About Dixile and Power Factory, you can able to see here what are the licenses available with this package. Okay. So for your information, generally the power system simulation softwares are work with fundamentally two types. One is the RMS and second one is the EMT. EMT means in simple words like a peak to peak. So Dixile and Power Factory, ETAP, PSSC and all will work based on RMS. EMT, PRV, PSCAD and all will work on EMT. Okay. So why we are using, how we are using, its matter. Result will be almost same, but there will be some difference between the RMS based simulation and EMT based simulations. This one we have to always keep it in mind. Okay, so in this single line diagram, what you are seeing is an wind power plant. Totally, this wind power plant having a 6 number of wind turbine generators. So each turbine is rated for 2.5 megawatt. Okay, so 2.5 megawatt. Totally, it is an 15 megawatt generation. So the wind turbine LV voltage is 690 volt, and its medium voltage is 20 kV. It is get interconnected to the medium voltage level only. The medium voltage level, the irradiation medium voltage interconnection, that also 20 kV. There is no substation to step up the voltage because it is connected to the distribution network. POC means point of connection, PCC means point of common coupling. It is a terminology used for a location of compliance. It is very based on the grid code or particular country where this project we are doing. Okay, so first we have to build the single line diagram. So this is an completed example. So here most of the details are already entered. So this is the first one. We have to build the single line diagram. So we have more. So in this one, 6 number of wind turbine generator is there. Corresponding transformer, wind turbine transformer also model. Then this one will be an collector network. Mostly this will be an cable. Just a minute, I will close this one. So it having two collector network feeder. So two wind turbine generator is connected to the main LV bus bar at 20 kV through one line. Another 4 turbines are connected to the LV bus as a second line, and also we are having one capacitor bag for the reactive power compensation. Sorry, it's loading. Wait a minute. It's in capacitor bag. So first, what we have to do, we have to build the single line diagram as per the steps. So single line diagram has been built. Then second one, the rating we have to enter. So the rating it's entered. So it's rated apparent power is 2.7 MVA, and its rated may have active power is 2.5 megawatt. Okay. Then wind turbine transformer. In the wind turbine transformer, it is 2.8 MVA. Its voltage is 20 kV at the high voltage side, 0.69 kV at the low voltage side. Vector group, high voltage side it is delta, and low voltage side it is star grounded. And its impedance, this one is the short circuit voltage UKH and impedance 6%, and it having the copper loss of 20 kilowatt. This is for the positive sequence, and the bottom one for the negative sequence. For doing the harmonic study, so we have to model both the positive sequence as well as the negative, zero sequence. So here, modeling of harmonic source. So wind turbine generator is the major source of harmonics. So we have to model the power quality page. We have to model here harmonics. So in harmonics, we can able to model multiple ways. One is the balanced method, and another one is the unbalanced method. Third one is the IEC method. IEC 61000 is a standard. So these values are modeled as per the standard. The left bottom one, it's an integer. That is our harmonic value, second order, third order, fourth order. In the right side, it is a non-integer. So it means 1.5 to 2.5. So what it means? 1.5 means it is 75 hertz. 70 from 75 hertz we are modeling. So it is an interharmonics. This is an integer harmonics. And there are some situation we have to model balanced method also or unbalanced method also and IEC method also. That depends on how much amount of data we have, how much amount of accuracy we want to model. Okay. So unbalanced method is a higher accurate method because all the three phases we have to include the current harmonic value as well as the phase angle. This one we have to model here. Phase angle we have to model. So particularly when the voltage, how much is the voltage and what is the angle it is oscillating. So that we have to model here. Okay. And about the impedance, so this is model as a Norton equivalent impedance. So here we modeled a source, that is a current value. Here in frequency dependence or one frequency dependent x1, frequency dependent R2, frequency dependent x2. So what it means is that R1 is a positive sequence, resistance and reactance of Norton equivalent impedance, and R2, X2 is the zero sequence resistance and reactance. I will open one value here. You can able to see for the harmonic value they had used 9999. So what it means is that they modeled a simulation such that the particular Norton impedance will not be counted in the simulation or calculation. So like that only they have modeled this one. For an accurate modeling for each harmonic order, we have to model this resistance and reactance. Okay. Then I will run the power simulation. So this is our point of connection. So at this location only we have to complete the simulation. So in Dixel and Power Factory there are some options is there, power quality and harmonic analysis. So harmonic analysis, and so we have to select balanced method or unbalanced method. So we have to select. So here I'm just running through the balanced method, just executing the simulation. Okay. So simulation will run and I will give the result. So the simulation has been executed. Here you can able to see, normally we will see the voltage distortion at the bus, current distortion at the line. So at this bus, what we are seeing is an voltage THT is an 0.71%. So current we have to see at this point. At this point, the current distortion here, the THT is 1.08% is the current THT at this location. So about the plot, I already mapped this one. So here we can able to see that current distortion and voltage distortion. Check this one. In the first curve, the first graph is an voltage distortion, and the top one is the voltage distortion, and the bottom one is the current distortion. So here you can able to see the harmonic spectrum. So in voltage, we can able to see fifth order is the dominating one. Then next dominating is the 7.5 order. In the current side, fifth order is the dominant one. After that, third order is the dominant one. Okay, so hereafter, now as of now we have computed the harmonic analysis. So after that, what we have to do, we have to compare this value with the allowable limit. So allowable limit normally will be available in the particular grid code document or a particular standard. IEEE standard 2800, IEEE standard, that is for IEEE standard 2800 for the transmission connected IBR plants. The harmonic maximum limit is available in 2800. IEEE 1547 for the distribution connected plants. Current harmonics available in that one. So what is that TRD percentage it is available given in the standard, how much is coming. So for that one, we have to comply, we have to compare the calculated value with the allowable limit. If everything is fine, then it is good. If some harmonic individual order is exceeding the limit or the TRD, the total rated current distortion, is exceeding the limit, means we have to modify our plant design. So the modification may be changing the inverter wind turbine manufacturer, one manufacturer to the another manufacturer, or changing or adding some harmonic filters. So here they included a capacitor fan. So the same one we can use it for the harmonic mitigation. And so here this is not a simple capacitor fan. This one they have modeled as a harmonic filter, passive filter. So it is at 0.25 ABR. It's modeled for 750. Okay. So it is an typical RLC filter. So multiple options will be available: RL filter or C filter, RLC filter with the parallel resistance, then RLC filter, yeah, and another combination. So multiple option will be there. So based on our requirement, we have to model the harmonic filter, and we have to perform the harmonic analysis again. So we have to redo the harmonic filter tuning until we get the compliance with the grid code requirement. Okay. So now we came to the end of this presentation. In this presentation, I have explained about what is power quality and different types of power quality as per IEEE standard 1959, and about the harmonics, how the harmonic is created by the nonlinear loads, and after that the different harmonic evaluation indices. Then after that, I have explained about performing the harmonic analysis for 180 kilowatt solar plant through the power quality analyzer. And after that, I have explained about performing the harmonic analysis through the computer-based simulation for 15 megawatt wind power plant. you have any queries, please unmute yourself and ask the questions. Okay, there is no queries now. If anything, if any queries in the coming in the later stage, when you are doing this harmonic analysis, I'm happy to support you. You please reach out to me in my mobile number through WhatsApp or through email. Yeah, that's about from my side. I'm happy to hand over the session to the organizer.
Thank you, sir. Dear participants, if you have any questions, you can ask now, or else we shall move on to the next session. Participants, sir has shared his contact details in the chat box. If you have any questions, you can contact sir directly. Thank you so much, sir. That was an excellent presentation. We have learned a lot about the harmonics from you, sir. Now I invite Arutra to deliver the formal vote of thanks.
Thank you, sir. Good afternoon, everyone. It is indeed a great honor to extend our heartfelt gratitude to our esteemed speaker, Mr. P. Sivaraman, for sharing his valuable insights on harmonic analysis for IBR plans today. With 10 years of experience in this field, his guidance has provided us with a clear perspective on the technical details and real-world applications of harmonic analysis. Sir, your session was not only enlightening, but also highly engaging, helping us grasp the practical challenges and advancements in power plant control. Your willingness to share your knowledge and experience is truly commendable, and we deeply appreciate the time and effort you have taken to be with us today. On behalf of everyone present here, I express our sincere gratitude to you, sir. We look forward to more such opportunities to learn from your expertise in the future. Thank you, sir.
Yeah, thank you, Arutha. If anyone needs any guest lecture for your IEEE student tracks, I'm happy to support. Please reach out to me. I'm happy to support any IEEE student tracks. Yeah. Thank you.
Thank you, sir. Thank you so much, sir.